Welcome to Data Science 1, Probability, Working with Discrete Distributions, Part 1. All right, so far we've talked about lots of things, and now we're going to start putting things together to actually calculate probabilities. If you look, I think we're up to like video number 21 or 22, so we've come a long way. And what do we know so far? We have lots of probability distributions that are discrete. And when I say discrete, I mean that the x value, the random variable, can only take on countably many values. Okay, and usually they're whole numbers, but need not be. They just are discrete events that are easily countable. All right, so probability distributions we've seen so far. We've seen Bernoulli, binomial, geometric, negative binomial, and the last video, Poisson. And we've seen simple examples with these. Now, what we'd like to do is be able to calculate more complex probabilities, and that's what we're going to do in the next two videos, is look at how do we put ideas together to calculate more complex experiments. All right, so typically we want the probability of a specific event. And the only events we've considered so far are just single values, but often we want a range of values. And the great thing about discrete distributions is they just add up. Okay, and that's why we've constructed everything the way we have, is so things just add together. So the probability that x is between A and B is probability that we start with A and end at B of the probabilities, and we sum them up. And you can write it different ways, but these are those ways. All right, so let's look at an example. Suppose Benoit is a lecturer giving a multiple choice test with 10 questions, each with 4 options that are scored as either correct or incorrect. Passing score is 7 or above. If a student simply randomly guesses at all of the questions, what is the probability they achieve a passing score? Okay, well, let's see. What do I know here? Well, I know that there are 10 questions, so this sounds like there's a limited number of trials, right? So that immediately makes me think binomial, okay? Because there's a limited number of trials, n is equal to 10. If they're randomly picking, remember there are 4 options on each question, then randomly picking would be 1/4. All right, and we're interested in whether they pass. So notice it's not just they get a score of 7, it's 7 or above. So this corresponds to the probability that we're greater than 7 is the probability we're equal to 7, probability we're equal to 8, equal to 9, and equal to 10, and we add those together. Okay, so we can use our density function or our distribution function that we played with so far, plug all the numbers in, and this is what it begins to look like. And notice, wow, this gets more complicated as we go along here. And notice that some of these, as we calculate them down, become very, very tiny numbers. Okay, so very tiny numbers. And if we come up at the end, we've got 0.0035. This is the probability that somebody would pass just by randomly guessing from the 4 options. So it's about 0.3%, 0.3%, or 0.0035. So it's kind of unlikely. All right, here's another one. An is interested in the number of patients who come to a clinic presenting symptoms of malaria, and he's interested in this across each day. From past information, the mean number of patients per day is 2.2. She wants to know what's the probability that less than 4 patients will present symptoms of malaria on a given day. So she's talking about who come to the clinic and present them, not just who are randomly in the population. Okay, so notice that there was a count and per day, so that makes this a Poisson experiment, and they said the mean number, and that should kind of give it away if it's discrete, that it's a Poisson. So lambda is equal to 2.2. Now, it's over a time, which is day, so we can just plug things in. So we have the probability that x is greater than, or less than 4. Okay, not less than or equal to 4. So you have to pay attention to this inequality, and that's why I did this example. Because it's 0, 1, 2, or 3, not 4, because 4 would be equal here, and we don't have equality there. All right, we plug this into our probability distribution function, do all the math, do all the work to get it worked out, and we come up with here that it's about 0.8213. So it's quite likely that there will be less than 4 patients that will present symptoms of malaria on a given day coming into this clinic. So it's pretty easy to work with if you just add things up. All right, so that's the idea, and that's the theme of this one, is probabilities can just add up. we need to be careful about inequalities, and we may need to use some other properties to calculate probabilities, and we'll do that in the next video.